The last two circuits were pure resistive and pure inductive. This circuit we have is purely capacitive. As we know, capacitors have a special property to hold the charges. It gets charged and discharged. The capacitor stores electrical power in the electric field. This effect is known as the capacitance. The capacitor consists of two conductive plates which are separated by the dielectric medium. It stores energy in the electrical form. The capacitor works as a storage device and it gets charged when the supply is on and it gets discharged when the supply is off. If it is connected to the direct supply, it gets charged equal to the value of applied voltage. If we apply an alternating current or AC supply, the capacitor will alternately charge and discharge at a rate determined by the frequency of the supply. Then the capacitance in AC circuits varies with the frequency as the capacitor is being constantly charged and discharged. We know that the flow of electrons onto the plates of a capacitor is directly proportional to the rate of change of the voltage across those plates. So, we can see that the capacitors in AC circuits like to pass current when the voltage across the plates is constantly changing, but it does not like to pass current when the applied voltage is of a constant value such as in DC signals. When we consider an AC supply, at 0 degrees, the rate of change of the supply voltage is increasing in a positive direction, resulting in maximum charging current at instant of time. As the applied voltage reaches its peak value at 90 degrees, for a very brief instant of time, the supply voltage is neither increasing or decreasing. So, there is no current flowing through the circuit. As the applied voltage begins to decrease to 0, that is from 90 degrees to 180 degrees, the slope of the voltage is negative. So, the capacitor discharges in the negative direction. At the 180 degree point, along the line, the rate of change of the voltage is at its maximum again, so the maximum current flows at that instant and so on. For capacitors in AC circuits, the instantaneous current is at its minimum or 0 whenever the applied voltage is at its maximum, and likewise, the instantaneous value of the current is at its maximum or peak value when the applied voltage is at its minimum or 0. From the waveform, we can see that the current is leading the voltage by quarter cycle or 90 degree. It conveys that in a purely capacitive circuit, the alternating voltage lags the current by 90 degrees. Now, if we look at the instantaneous voltage and current expressions,
the alternating voltage applied to the circuit is V equals Vm sin omega t. Charge of the capacitor at any instant of time is given as Q equals Cv, and then current flowing through the circuit is given by the equation I equals dq by dt. Putting the value of Q from the earlier equation, we get I equals d by dt of Cv. We will substitute the value of voltage V from the equation of voltage. Then the expression looks like this. On differentiating and simplifying, we have I equals d by dt C Vm sin omega t. We have substituted the value of V here, which will be equal to C Vm stays out of differentiation as they are constant. So, we have C Vm d by dt of sin omega t. On differentiation, we have I equals omega CVm cos omega t. Differential of sin omega t is cos omega t. We can further simplify this expression as Vm divided by 1 by omega c into sin of omega t plus pi by 2. We have purposefully written 1 by omega c here. The final expression will be I equals Vm divided by xc into sin of omega t plus pi by 2. Xc will be equal to 1 by omega c and is the opposition offered to the flow of alternating current by a pure capacitor circuit and is called capacitive reactance. The value of current will be maximum when the expression sine of omega t plus pi by 2 equals 1. Therefore, the value of maximum current Im will be given as Im equals Vm by Xc. Substituting the value of Im in the equation, we will get I equals Im sine omega t plus pi by 2.
The last thing is the power and power curve. Power is given as V into I. So, P is equal to Vm sin omega t into Im sin omega t plus pi by 2. So, P is equal to Vm Im sin omega t into sin omega t plus pi by 2. On simplifying, Vm Im sin omega t into cos omega t. Because sin omega t plus pi by 2 is cos omega t. We can make use of trigonometric formula and write the expression as P is equal to Vm Im divided by 2 into sin 2 omega t. We have used the formula sin 2 omega t is equal to 2 sin omega t cos omega t. As we can see, if we calculate power over one complete cycle, it will be 0. Because in the power expression, we have sin 2 omega t term which is periodically varying, and the values of it in the positive half of the cycle will cancel out the values in the negative half of the cycle. We can conclude that power consumed in a pure capacitive circuit is 0. This is all about AC circuit with pure capacitance. To sum up, we learnt about the property of holding the charges by capacitor, how it discharges and charges when we have AC supply. Also, the current leads the voltage in pure capacitance circuit. We also learned expressions for instantaneous voltage and current. And finally, the net power absorbed is 0. In the next video, we'll look at a circuit which has resistance, capacitance and inductance in that circuit. See you there.